Hi, I'm Ryan Baker, and this is Big Day in Education. In this video, we're going to talk about tweaking your model towards optimality. So the first method we're going to talk about in this space is called SMOTE. SMOTE is something you use when your data has a really bad class imbalance. For example, maybe only 3% of the training labels are the class that you want to predict. And many algorithms are going to bias in favor of predicting the 97% over the 3% because most goodness metrics, even things like kappa that are supposed to control for this, are going to reward the algorithm for doing better on most of the data than just a little bit. SMOTE is a simple approach to addressing this, which clones data points from the rare case. It can also remove data points from the common case, although it's used this way less often. And SMOTE can lead to mildly better performance. It's one of those things that makes a little bit of difference. I often find it gets us like 0.02, 0.03 better. Worth doing when you've got these imbalanced data cases. Not going to turn a junk model into a perfect one. When you use SMOTE, it's really important you always need to make sure to conduct SMOTE only on your training set. Don't clone the data points in your test set. If you clone the data points in your test set, your model performance estimates will not be representative of real-world conditions. And I've seen a lot of papers where when they do this, they actually get these glorious performances because they're overfitting. Also, make sure that you don't have the same cloned data points end up in both the training and test set, because that really leads to spurious better performance. So SMOTE, totally a safe method to use, totally a good method to use, but make sure you use it right or you'll do silly things. Now, one note about SMOTE, and this really applies to any algorithm that changes the distribution of your training data, it's going to mess with your probability estimates, driving them towards 50%. And when does that matter? It mostly matters when comparing classifiers to each other, because if you've just got a single classifier, as long as you're not using a default cutoff, as long as you're like looking at a precision recall curve to choose your cutoff, or comparing probabilities to each other within that classifier, it's all good because you've adjusted everything the same way. If it turns out to matter because you're comparing classifiers to each other and you want to make sure they're on the same scale, there's a lot of simple hacks. The simplest is probably just to fit a linear function to map the confidences back to the original proportion. So in other words, if the original proportion was 3%, but the average confidence is now 16%, fit a linear function on the confidence to get it back to 3%. You could set an offset and then kind of threshold at 0. You could set a slope. Couple things you can do, not really a big deal. You can also fit a spline curve to do this more smoothly. It's a lot more work. Or for cases where what you really care about is that the proportions come out right across multiple classifiers. So you want that 3% for this construct and 8% for another one and 15% for this one over here. What you can do then is to fit and rescale each classifier's confidence to the value such that the final proportion comes out right. Bottom line is, rescaling is something you don't have to do very often. I've probably done it like 3 or 4 times in all my career. But it's useful to think about when you need it. Sometimes you need it after doing SMOTE, and there's a lot of ways to do it, all that are fairly simple. As an alternative to SMOTE, various papers have experimented with different forms of synthetic data generation. Things like trying to create new data points that look like existing data points. There's been some increasing recent interest, including in my group, in using generative AI, large language models, to do this. Watch this space. I got nothing to put up here right now, but it's a fast-moving area, and by the next time we revise these slides, probably about a year from now, this will be different. Okay, so those are some of the things you can do when you have a class imbalance. But what if you don't have a class imbalance? Your model's just not that good. Or what if you address your class imbalance and it doesn't fix things enough? Another thing people will do in tweaking towards optimality is to look at the cases that the model fails for and conduct further feature engineering to capture those cases. Slater et al., for example, proposes a method involving visualizing cases the model fails for to help to analyze why it might be failing for those cases. Now, when doing this, it's really important to hold out a test set. If you look at performance on your current test set, take cases from your current test set, and see where it doesn't work, redesign features for that test set. It doesn't matter that you're building the model just on your training set. You've secretly, quietly human overfit. As some people call it, it's not gradient descent, it's graduate student descent. So you always, when you do this kind of thing, you want to hold out a test set. Another thing you can do to improve your performance is use hyperparameter tuning. Most contemporary and for that matter, classic algorithms, have hyperparameters, parameters that govern the algorithm's search space and eventual type of model it chooses. They have hyperparameters that govern their behavior. Hyperparameter tuning can lead to much better performance. Things like trying different parameter values and seeing if the data fits better. Things like grid search or iterative gradient descent. And again, it's important to hold out a test set. If you do this, especially if you do this on cross-validated goodness, you'll massively overestimate your model goodness this way. And again, people talk about graduate student descent, where the grad student sitting in the lab tries 3,000 different parameter combinations and finds the one that works. In general, you always want to hold out a test set when you do these kind of things, because you want to make sure that you haven't just massively overfit on the space of possible models. So another thing you can do, modern foundation models based on neural networks allow what's called fine-tuning, which is where you take an existing foundation model and then you add some new examples, for example, for your specific case, for your specific problem, and you take that foundation model and you train its last output layer of the neural network to fit them. And this can be a powerful tool for getting new behaviors out of existing foundation models and improving model performance. It really can make a big difference compared to zero-shot approaches. Relatedly, you can fit a model and then have it label cases and have a human being give input on whether the model is correct, which then becomes additional training data. If the model is labeling cases it's uncertain about, or it just presents cases that's uncertain about for labeling, then this becomes active learning, which we'll discuss next week. So in other words, there's kind of the reinforcement learning case. We'll talk more about reinforcement learning much later in the class. But there's the reinforcement learning case where the human says, no, you got this wrong. This is the correct answer. And there's the active learning case where the model says, I don't know what to do here. Both of those can be really useful for getting your model to perform better. So those are a few of the ways that you can tweak your model and make it better. And it's the kind of thing that people spend inordinate amounts of time on because they want to get the best model they can. In our next class, we're going to talk about what I mentioned a second ago, active learning and its close cousin, transfer learning. See you in that video.